The second portion of our exploration of water wells and groundwater in general will be on groundwater, what I'm calling sources, and where the groundwater comes from in some fashion, how we extract groundwater for use in drinking water or other potable supply needs. So we'll start again focusing on groundwater itself. As we've said, uh, groundwater by definition is water in the saturated zone, water that's present beneath the Earth's surface within the soil pore spaces or fractures in rock formations that result in saturation. It may be the result of infiltration or percolation of water down to the water table through soil and cracks and consolidated rock, but ultimately in the saturated zone, all of the spaces, pores, whatever they may be in rock or soil, are filled with water. And as you can see in the picture, the area above the water table, and as we said before, the definition of water table is the top of the saturated zone, and the area above that is not saturated. There may be moisture, there may be some water, but it's not saturated and it doesn't move freely, nor would it provide any source of supply in any real productive fashion. One of the things about groundwater, it's going to flow with the slope of the water table. Now, that slope of the water table may not necessarily be consistent with the slope of the ground above it, but groundwater flows relatively freely, though in some cases slowly, through aquifers. It's going to flow downhill, so to speak, with the slope of the water table, depending on what's going on with the water table. Ultimately, groundwater is looking for an exit point. Eventually it drains into streams, rivers, lakes, oceans, but again, it could flow in a different direction than the ground surface, depending on what's going on. From a water quality standpoint, while groundwater is a reliable, in some cases accessible, and often inexpensive source of supply, it is subject to potential water quality issues. So the contamination of groundwater is something which we need to be particularly concerned about. And depending on where the water is flowing, if there's a source of contamination upstream of the flow of the groundwater, then it ends up in the supply source. In some cases, the flow of groundwater can change, as you can see in the picture, where you've got water that normally is flowing one direction, but then suddenly there's a well operating and draws water the other direction and can create some issues. So the types of things we're concerned about can be just natural contamination underground, but man-made landfills, waste storage ponds, septic systems, different types of agricultural activities, any kind of illegal dumping, any contamination perhaps of water that we're potentially using for recharge, which we'll talk about in a bit. So this exhibit kind of shows a lot of those different things. You've got landfills, you see leaking sewers as a potential for, as that gravity draws that down potentially to the water table. Septic tanks, pesticides, all sorts of things that end up on the ground that can ultimately percolate down into our groundwater supply. We need to be real careful about monitoring for those types of things to ensure that the drinking water supply that we're counting on doesn't end up contaminated. Some of the factors that can impact the groundwater and potential for contamination can be the distance from a well or a point where we're extracting groundwater to whatever that source of contamination is. So obviously and intuitively, the further away that the contamination is from our let's just say well, then the more protected it might be. There is not a set distance in regulations. There are other factors that are going to drive it as well, one being soil conditions. How quickly can a plume of whatever contamination might be move through the system? The slower it flows, the more time you have. The other thing that will drive it is the flows themselves. What direction is it flowing? Is the source of contamination upstream of our well? And what direction and how that those will impact as well. So those factors really include, again, how far is it, what soil conditions and how conducive they are to flow, and then the direction of flow will impact the potential for contamination of our groundwater. Groundwater basins that provide a source of supply, we're drawing water out of them, they have to be recharged, or you have an overdraft condition. I mentioned on the Orange County groundwater basin, they specifically limit how much water can be taken out. All of the agencies that have access to the groundwater basin are limited by something called the basin pumping percentage, which tells them they can only get a certain percentage of the water from that groundwater basin. Maybe it's 60%, maybe 65, 70%, depending on what conditions are. And so they have to have other sources of supply. If they don't do that, if they on a basin that's managed like this one is, then you can continue to draw the water level down to a point where it's no longer sustainable for anybody. So managing those basins becomes really important. There are sources to recharge the basin. As we take water out, water comes back in. Of course, one of the most important is natural recharge, where you have groundwater coming through just the hydrologic process, water moving downward from the surface to recharge it. So it's precipitation, it's rainfall, it's snow, and it's ultimately seeping down through the non-saturated zone, ultimately into our saturated aquifer to recharge it. And to the extent that our natural recharge keeps up with the amount of water that is being taken out of the basin, then everything works just fine. When that's not happening, then we have to be a little more aggressive and proactive with some sort of managed recharge. And when we're talking about managed recharge, we're talking about intentionally adding water to the groundwater basin through injection wells, where you're literally pumping water down into the groundwater basin to provide to intentionally enhance the supply in the basin to recharge it. There are also recharge basins where, as you can see in the picture here, you're providing either, in this case, directing a stream flow, in some cases specifically adding water to a basin that will then spread out and percolate through the ground and ultimately down into the groundwater basin. That is still a natural source of supply, just directed in that area, but there are also projects, and one of the biggest in the world is the groundwater replenishment system, the partnership between the Orange County Water District and the Orange County Sanitation District, where they are taking wastewater, sewage, treating it to an extremely high level, and then pumping that water up to recharge basins to recharge and to provide supply into the Orange County groundwater basin. And so the technology certainly exists to treat wastewater to drinking water standards. It's a combination of microfiltration, reverse osmosis, ultraviolet disinfection. That process produces essentially very near to distilled quality water. It's better than a lot of drinking water. So the technology certainly exists to do that. The Orange County groundwater replenishment system currently has a capacity of 100 million gallons per day, and they plan to expand it to 130 million gallons per day. So it's a fantastic project. Again, one of the biggest in the world. There's a huge amount of benefits to it. It's very cost and energy efficient. It's producing water at maybe $525 an acre foot with subsidies, maybe $850 or so without the subsidies. Compare that to the cost of imported water that's over $1,000 an acre foot. So it's actually cheaper than imported water. It takes maybe half of the energy to produce and deliver this water than it does to import water from Northern California and the Colorado River, and a third of the energy of desalination plants. So it's both cost and energy efficient. It provides what is basically a drought-proof water supply. Obviously, you're treating wastewater to drinking water, so it reduces the amount of wastewater discharge to the ocean and helps to manage the overdraft of the Orange County groundwater basin. So it's a great project. In addition to that, it also helps with the seawater barrier. thought I had a picture, but maybe that's the one I want. So this one shows an injection well, basically. And what they're doing, in addition to providing water to the recharge basins, is one of the problems in the Orange County groundwater basin is as they draw water out, it's near the ocean, and seawater wants to intrude into the basin. And you cannot obviously have the seawater in the which is essentially a contaminant. It's obviously, from a salt standpoint and everything else, it's not conducive to intrusion into the groundwater basin as far as the drinking water supply goes. So one of the things that they do with the product from the groundwater replenishment system is a seawater barrier, basically. So they inject the water into injection wells, a whole string of them, near the coast, to provide a water barrier to prevent seawater from coming into the groundwater basin. And then, like I said, the rest of it goes to the recharge basins up in Anaheim, the Anaheim and Orange area. So it spreads out. There's 3 basins up there with a total surface area of around just under 70 acres and a capacity to recharge of about 83,000 acre feet per year. In order to do that, though, the plant that produces the water is about 13 miles from the recharge basin. So they had to build a 13-mile long, 60-inch diameter pipeline that has a capacity of about 80 million gallons per day to get the water from the plant up to those recharge basins. So all told, expensive, but to build the project, but ultimately, when you aggregate it over the amount of water that it's producing, produces water that's cheaper in cost than is the water from the import supply sources. So next thing I want to talk about is briefly is springs. The springs, by definition, is an area where the water table intersects the ground surface. So water basically flows out of the ground naturally. This picture here, I like, you've seen it before. It shows the aquifer, but up in this area over here on the top left, it shows the aquifer intersecting the ground surface. So water's basically flowing out of the ground. That is what a spring means. You get the side of a hill, a valley at the bottom, or maybe even an excavation that intersects with a flowing body of groundwater at or near the water table that is going to produce water flowing from out of the ground. That's a spring. Anytime an aquifer is filled to the point that the water table overflows to the land surface, you've got a spring. And so some things to be considered when you're talking about springs: they're going to have relatively minimal capacity. They're not going to be able to produce water at a high level in terms of volume. They typically do not have adequate capacity to serve a public water system. You also, and just another picture that kind of shows that intersection of the aquifer with the ground surface, just to kind of drive home that concept of where a spring comes from. But one of the other things to be considered is you have the same kind of water quality issues, perhaps more so, because now with the water quality things we talked about before, you had perhaps the confining layers of a confined aquifer to help protect. You had perhaps some depth to help protect the water. By definition, a spring is going to be relatively shallow. It's where the water is coming to the surface, so you have no idea where that water is coming from. Is it in fact an underground spring, or is it seepage from a nearby septic tank? So the surface water treatment rule says that springs and other sources of supply, like infiltration galleries, which we will talk about in a moment, they have to be treated the same as surface water. So regardless of the fact that it is to some extent underground, they still require treatment and filtration. The collection of water from a spring comes through what's called a collector box, typically some sort of concrete box that you've got that's going to be installed near where that spring would typically exit. You're going to have to make sure that it's protected from contamination and things like insects, animals, and certainly any kind of surface drainage. So lots of water quality analysis would need to be done to make sure that the water remains safe to drink. One other means of extracting groundwater is what's called an infiltration gallery. An infiltration gallery is basically a system of buried perforated pipes near a some sort of water body, maybe it's a stream or a river, that are collecting some level of partially filtered surface water. But once again, you're going to have a similar water quality concern, a similar contamination potential. And so the surface water treatment rule, again, will require treatment both for springs as well as for infiltration galleries, and really are treating the water just as if it was surface water. So again, which means treatment means filtration. So that is the discussion regarding some of the different, really focusing on groundwater and some of the means, not counting wells to get groundwater to extract it. The next section we will go into will focus more specifically on wells themselves.